Wise Wednesday. Paul Kwiat is helping us understand how the effects of COVID-19 may change in the upcoming summer months.
So let's get right to it. Okay, so my goal today is to try to combine all the things we've been talking about to try to get some understanding of why it might be that there's a seasonal variation to the coronavirus. So trying to answer the question, will it go away? And I'm not going to answer that question at all. In fact, a disclaimer, of course, I'm a physicist, not a doctor, nor an epidemiologist. Second thing is that I think no one really knows the answer to that question yet. For example, already in Singapore to date, there have been approximately 30,000 cases, and that's a place we would think of as being somewhat summary. Nevertheless, there was a recent University of Maryland study that showed that the virus has been observed to spread more rapidly in places with fairly cool temperatures and low relative humidity. So I'm going to try and connect that with everything that we've talked about for the last several weeks. So just as a reminder, when you cough or when you sneeze, you emit water droplets, and those range in size from tens to maybe up to 100 microns, something like that. And in principle, those could then be carrying viruses. We don't know how many viruses you need in order to get sick, so we don't know what size droplet is necessarily relevant. But just remember that sort of scale from 10 to 100. Another thing we know is that if I have two objects in vacuum, they will fall to the ground at the same rate. So if I take two objects, a droplet that's 100 microns in diameter and one that's 50 microns in diameter, and I drop them from 2 meters high, they'll hit the ground, both of them at the same time at just over half a second. Okay, the thing that we started talking about several weeks ago was the fact that if I have air resistance, the drag from that is going to lead to a terminal velocity. And in fact, we discussed in the second week that if I have small droplets, instead of turbulent flow, I have laminar flow, and that will actually lead to a much lower terminal velocity. So what is the impact of that? Well, if I don't have any air, then my particles will just both drop at the same rate. But if I do have air resistance, then they're going to be slowed down by the drag. And in fact, the 50 micron droplet is going to be slowed down quite a bit more than the 100 micron droplet. Okay, so we'll come back to that in a minute. But basically, they're staying in the air quite a bit longer. Okay, last week we were talking about evaporation, which is just the process where I have a liquid and water molecules leave that liquid, they go into the air. I said it's not a very good model to think of that as just being a one-way process, that really there's a trade-off. I have water molecules that are leaving the liquid and going into the air, and at the same time I have water molecules that are leaving the air and going back into the liquid. As long as I have more molecules leaving the liquid that are coming in, I'll have a net evaporation. And that's why we saw that there's an effective humidity. The higher the humidity, the more water molecules I have in the air above the liquid, and therefore that's going to slow the net rate of evaporation. Okay, so we'll come back to that in just a second. So this is a plot of my two water droplets, the diameter of the water droplets as a function of time. First, if there's no evaporation. So if there's no evaporation, then they just stay the same size. But if I turn on a mild evaporation, then we see that these water droplets are going to shrink because they're evaporating. And in fact, the smaller one, the 50 micron one, is shrinking quite a bit faster than the 100 micron one. That was with mild evaporation. If I have even heavier evaporation by another factor of 2 or so, then in fact, we see that these really start to shrink at a much higher rate. So now what I want to do is combine that with the fact that they're actually falling. So now we're going to have droplets that are falling and maybe evaporating. So this is the same thing I showed before. When there's no evaporation, that the 100 micron drop hits the ground in about 7 seconds, and the 50 micron drop in something like 27 seconds. That's with no evaporation. But when I turn on evaporation, because the droplets are shrinking as they're falling, and that has a lower terminal velocity, then they tend to hang around in the air. It doesn't have much of an impact for the 100 micron droplet, but it definitely has an impact for the 50 micron droplet. And in fact, if I have heavy evaporation, we see that it falls not really very far, and it's suspended in the air. And in fact, if there's wind or there's air conditioning, then in fact, those droplets can stay around for quite a long time. Now, because the evaporation happens more quickly when I have drier air, I can make now the connection with humidity here. So as I have less humid air, like in the winter, I'm going to have more of this evaporation, and my water droplets are going to be suspended in the air for a longer amount of time, potentially making them more transmissible. Okay, so that's a potential plausibility argument for why we might see a seasonal variation, but I should say that this is a very complicated problem, and there's many unknown um, factors that I haven't even discussed. Things, for example, like the salinity of the droplet as it gets smaller. So I think the true statement is there are still many unanswered questions. And to quote Albert Einstein, the important thing is not to stop questioning. We need to keep doing research on these things. So maybe the more appropriate modified quote from Albert is the important thing is not to stop social distancing. So I hope you guys all have a great week and stay safe. Bye-bye.